You've been hearing Dave's little mentions earlier. We've got a little bit of a preservation team ongoing. We've been picking up discs left, right, and centre, imaging them, archiving them, recovering the data from them. And for this, I figured I'd give you a little bit of a rundown on the equipment that we're using for that, or at least I'm using for that, and what we've managed to achieve. Well, not in great detail, it's only 20 minutes, but I'll show you what you can do yourselves to archive your own discs, how you can do that. So I'll just pan my camera down so you can see my little stack of kit. I've got a slightly unusual disk imaging setup. So that box on the bottom there in the clear plastic case is a disk ferret disk analyzer. So that can read and write from floppy disks at the level of magnetic transitions. So what are called flux reversals. So it's one flux reversal is when the polarity of the magnetic field on the disk goes from north-south to south-north. You get a pulse in the coil on the head, and that's you get an electrical signal that then goes through the what's called the read channel, the read amplifier of the floppy drive, and then down the cable as ones and zeros, one representing that there has been a transition. So you just measure the time between them, and that is the lowest level of data that you can store on a disk. There's encoding on top of that, which represents the actual binary ones and zeros, and then above that you have things like sector headers that allow the disk controller to sync up with the data and recover it. So that gets us the data off the disk at the lowest level possible, and that zips down a USB cable into my PC. On top of that, the minute being as I'm doing Archimedes archiving at the moment, I've got two 3.5-inch floppy drives. There's a Sony on the top, and underneath that a Panasonic. The reason I've got two is we found recently that although the Sony drives will get kind of 99% of discs imaged fine, there are some marginal ones where a different drive from a different manufacturer will actually read a disc that the other drive will not. Or we'll get, for instance, one track will be bad on one drive but will read fine on another. So we do the imaging with two different drives. You know, we've got a better chance of recovering the data. So I'm going to grab the next one out of my pile here. These discs I have here are all from one batch that was bought on eBay as a job lot of ex-school software. So it's all educational titles. That's a set of screens for my world. So to start with, this goes in the drive, and I'll turn on I'll leave that out of the drive so I can read the label on it. So I'm just going to share my screen now, and you should be able to see what I've got on here. So this little terminal here is running the disk ferret software, which is called Magpie. And what I'm telling it at the moment is just to grab, what is it, My World 2 screens for shape nets. And because it's a disk that's been made by the user of the machine, basically, I'm tagging it as a backup. So in the drive it goes. And just to give you a rundown, I'm telling Magpie that it's talking to a PC 3.5-inch drive as drive A, 100 megahertz clock rate for the counter in the disk ferret, do 2 reads of the track. So we've got 2 copies of the data as it goes around. It'll go around twice and record both revolutions, and then save it to this file here. So that's just, it's measuring the speed of rotation, which for a 3.5-inch drive is going to be 300 RPM. Because I'm feeling a little bit lazy and I don't want to wait for this 10-minute process to run, I'm going to load a disk that I got, that I imaged earlier in true Blue Peter fashion. So this software here is HXC floppy emulator. And all I've done there is dragged the image from the disk ferret onto there. It's running away and imaging the disk. It's looking at the disk image and it's analyzing what's in there. You click Track Analyzer. To get this, you click View Mode Dummy Disk here. There are a couple of different versions of this view. Dummy disk will use the whole sort of diameter of the disk, so you can see all the tracks quite large. The other formats will actually represent the fact that there's a margin between the edge of the disk and the first and last tracks. So just a little bit more accurate to what is actually on the disk and where it is. So we can see that we have two sides of the disk imaged. All of this is green, so it's read fine. The light green here is a sector header. The green here is a data block, and the dark blue is a gap. So that is those are there so that there's a little bit of tolerance for turning the write signal from the head on and off, so it doesn't overwrite data in other sectors if the disk rotation speed is a little bit slow or a little bit fast. It's just adding for tolerances there. So if I click on a track, it moves to the track view, and I can hover over a sector on the disk, and I can see that there is data there. These are ADFS disks, so sector 2 on head note and track note is the root directory, and we can see the root directory header there, the name Nick, the file names in that directory. We just scroll through with the scroll wheel, and then it's all zeros to the end because there isn't really much on this disk, other than it being it's a My World Screens disk. What have I got that might be a little bit more interesting? I'll load this one. So I'm hoping, I haven't actually looked at this one in great detail, but this is a Shurston software disk, a crystal rainforest, which I'm sure many of you will know from school. And if I look in the analyzer, yeah, well, I didn't have to look very far. That is, if I switch to the stream view, this makes it a little bit more obvious what's going on. The track view does some pre-processing to make the data a little bit more, I'd say, readable or understandable. If you go onto the stream view, things like copy protection become a lot more apparent because it turns off HXC's pre-processing. So we can see here we've got a fairly normal ADFS disk header, root directory, and then all of a sudden we have what looks like a chunk of random data, which doesn't line up. You can see that we've got the timing values tend to fall within certain bands. So we have a bunch of ones clumped together. We have a 1 followed by a 0 or a 1 followed by 2 zeros. And then in this track, it's just random. In this sector, it's just random. That's indicative of copy protection. We can also see it's gone red. That means that the HXC software has tried to decode that sector. And you can see on the right there, data CRC, bad CRC. CRC is for checksum. The checksum is bad. This is the kind of the intent of copy protection. It's created something that if you followed Chris Evans's previous talks on Disk Beast, this is kind of how a lot of copy protection schemes work. It's creating something that you can't write back with a standard disk controller. Just pop to the dummy disk view. And you can see there that it's indicating, where are we? Track note 1. You can see that our error is indicated on this block here. This is that sector we were looking at. But the interesting thing as well is that the red marks here are where HFE thinks there are write splices. So a write splice is where the disk drive has started or stopped reading. It's a discontinuity in the timing. So it's indicating that to us, that it's seeing quite a lot of those on that last sector of the first track. So it's another indication that we might be dealing with a copy protection scheme here. And this is the reason we do the imaging with a flux imager, like a disk ferret or a Greaseweazle, or indeed the Cryoflux. I'm not sure if Disk Beast counts as a flux imager. I think that just uses the disk controller, but at this level, all things become transparent. We can see everything that's going on. We can then export a disk image, so we can create an ADF file. If you select raw sector image and then stick .adf on the end, this isn't going to work in the emulator, but I'm just saving my temp directory, an ADF file. We've created an ADF file. The keen-eyed among you might have noticed I've imaged 81 tracks on this disk. Just to recap, if you missed Chris's last talk, that's because on some disks, the innermost track actually contains mastering data. Now this disk doesn't have it. We've just got a red track on the inside there. It's just unformatted. So I go to 80. Again, stream view, it's just random data with no headers. But on some disks that would store mastering data, which is, for instance, the data from the disk duplicator that says this disk was duplicated in this duplicator on this date. That can be useful for figuring out when a disk was written, when it was mastered. I think that kind of goes through the basics of this. You can see how we can get images out. We can also create HFE format images, which are more useful if the disk has copy protection. You've got these will load straight into a Gotek disk emulator on a physical Archimedes machine, so you can run, Crystal Rainforest or whatever from a USB stick, effectively, copy protection and all, and it's just storing that accurate representation of what was read from the disk. This is one of the disks we've been working on, and I'm going to pick on it because it's a bit of an extreme example. This is from the source code disks that we got donated from Matthew Atkinson via several other people a few days ago. Myself and Chris Evans have been working on these quite a bit. So first thing you notice is that HXC is struggling a bit trying to figure out what's on this disk. The reason for that is it's a 40-track disk that's been written in an 80-track drive with double stepping. So every other track contains nothing. The other thing is it's a single-sided disk. So HFE is trying to figure out what's going on side one, and it's just random noise. So it's trying valiantly to figure out what's happening there, but there's nothing. And in fact, I've made a mistake there. This is actually a 5 reads disk, so I just need to quickly change the setting here for this to load correctly. And we'll try that again. So the problem there was that this was imaged at 25 megahertz, so we could get 5 rotations worth of data out of there at slightly lower resolution. Unfortunately, the HXC software doesn't detect the clock rate from the file, so you have to tell it what it was. Hence why these files all have 25 megahertz 5 reads in the file name, so we know what settings to put in to get this to read out. So I mentioned the disk ferret just briefly. Then I have some PCBs left. They are, if people want to build one, I have PCBs available. Just a quick plug, drop me an email. I have some parts, but These days, I would suggest going towards Kia Fraser's Greaseweazle, as it's a much cheaper product and will do just about the same thing a disk ferret will do for you. Certainly, if all you're interested in is floppy disks. So you're probably talking about the £50 range for a Greaseweazle, a floppy drive, all the cables and power supplies that you need. And Kia Fraser is actively maintaining that. So if you're wanting to get started with this, that's what I'd recommend. So you can see here we've got the stream view popped up. If I load up the dummy disk, I'm hoping this is the one that has the big scratch in the middle of the disk. No, okay, I've picked the wrong image. But again, you can see that we've got something that looks like it. If I load the right view. Have I just crashed this? No, it's loaded. Or has it? Right, there we go. It's recovered. We've got something on track 0 that looks like it could be copy protection, but it's not. This is actually disk damage. It's either a weakened magnetic field or it's disk corruption. So the key thing to notice here with this versus the copy protection is it still falls into the 2 bands, but the gap between them is very fuzzy. So what this tells us is that this sector has been written either on a disk drive with very poor speed control of the rotation motor, or the magnetic field has gotten weaker over time. And you can kind of see on the sectors adjacent to it, we see the same kind of peak shift and offset that we see here, just not to that much of a degree. So this is the sort of thing we would have to sit down and the general ways to approach this are you either have a second copy of the disk that you image, or you sit down and look at the individual transitions in a very slow process and try and decide whether they're more likely to be a 1 or a 0. This disk actually reads much worse on a TIAC drive than on the Mitsubishi drive sat in that Vigeland box there. So this is the reason we have multiple drives. We did a second read on this. This is that second read. But we also have, I mentioned earlier, there are 5 copies, 5 reads on there. So I can scan across, and sometimes you get lucky. Sometimes one read will be significantly better than the others and will decode almost perfectly. We've not been that lucky this time. You can see there is a kind of a general trend of things subtly improving, or at least not getting any worse. So there are things we can do like averaging out the different reads, statistical analysis, stuff like that, going really deep into it to recover this data. And that's why we do 5 reads, try with different drives. So hopefully I wasn't too technical there for you, but that gives you an idea of what we do. Perhaps not why we're doing it, but I hope that's kind of apparent. We're trying to get this lost source code back, and these games and application programs that have been thought to be lost that have turned up in someone's shed, loft, garage, cupboard, etc. And we're trying to archive it for future generations to explore and enjoy. There's a computer museum could set themselves up with some BBC micros and Archimedes machines and Gotex, and you could go in on a weekend and show your kids, Crystal Rainforest, here, play it. This is a game I played in school, and they can sit there and enjoy it just like the older folk here were able to themselves. So I think that's about all I was going to go through. Any questions?
Yeah. So you've captured all the data there, and as you show, in some instances there'll be corruption or even, I suppose, obfuscation with copy protection. So how do you then go from there to either I suppose, decrypting any copy protection, or perhaps worse still, recovering data that's corrupted?
So there's two separate questions there. We wouldn't normally, you asked about decrypting copy protection. Normally you wouldn't. If you just want to run the disk as it is, then you create a HFE file, and that will accurately store what was read from the disk, including the copy protection. So, for instance, Sherston tend to use what's known as weak bits, which is basically a block of data that will read differently every time. Because we've duplicated the timing of those bits, they kind of exploit a timing error in the way the disk controller works. Because we're playing that data back to the disk controller the same way with the GoTech, it will see them as weak bits in the same way. So we don't really need to decrypt the copy protection in that sense. Not in the same sense you would have to create a recording spec file for ADFFS. So we don't have to. For recovering data, there are a couple of tricks in our arsenal. I mentioned a few of them. Like I said right at the beginning, reading the disk on several different types of drive is one trick that we've used, and that sometimes bears fruit. But the bare disk in there, you can just pull the shutter back on a floppy disk. We found disks that have had dirt and mold on there and have just not read. And the easy way to fix that is, if I dig in my cupboard for a second, we just hold the shutter open, a pack of foam swabs, and a bottle of isopropyl, and just move the disk around. There's a little 3D printable hub that you can get, and a little holder that will hold the disk shutter open, and you just go through the disk under a bright light with a microscope, or a strong magnifier will work just as well, and you just look for bits of dirt and scuffs and damage on there, and just clean it off. We tend to do that as a first step if we know the disk has been stored in kind of adverse conditions, just to make sure it's not going to get dirt and grime on the disk heads of the drive, or worst case scenario, actually damage the drive if you had something like sand or grit on the disk surface. Try different drives is one trick. Reading the disk several times in one revolution is another. Cleaning the disk is another. A much gentler way of doing that we generally prefer. With 5 1/4 inch discs, I haven't got one to hand, unfortunately. What we typically do is open the disk jacket up by slitting it along one side, taking the disk out, cleaning it with fairy liquid and warm water tends to get used quite a lot, because that's a lot gentler than alcohol, less likely to take the surface off the disk. We would then get a donor disk, which is known to have been stored in a clean place. Again, slit the side of the jacket open, remove the disk from there, check that the sleeve inside is nice and clean, and then put the disk in there. What I tend to call the cookie, the actual magnetic floppy disk itself. Put that into the donor sleeve, into a drive, read it, and there you go. It's a one-way process. You can't easily put the disk back together, and it's one that we'll do as a last resort. It does tend to ruin the kind of collection value of the disk. We'll do it because we're more interested in the data. Does that answer your question?
I think yes, certainly. Yeah.
Probably in a little bit more detail than you're expecting,
No,
possibly.
that's fine. But the interesting thing is, most of your recoveries is at the physical level, by the sound of it, as opposed to, you know, I suppose trying to delve into bits and bytes at the software level.
Yeah, we sometimes have to do that, but we haven't had to do that yet, which is a bit of a roundabout way of saying we know how to do it, but we haven't had to do it yet. So there are things I've touched on, things like statistical analysis we can do, and if we've only got one errored bit, if it's very obvious from that, if I just pull up the track analyzer and resume screen sharing, if we have a little bit where there is just one spike in the middle of a sector that is very obviously an error, and it's the only error on that track, what we can do is look into how that decoded, and if it decoded as a 1, we can flip the bit and decode it as a 0 and see if that improves things. On this kind of statistical and software analysis point of view, I said we can average multiple reads. If we're getting noise over the data, that can help. We haven't actually tried that out yet. That's theoretical. The other thing is sometimes you can look at the data on the track and you'll immediately see that, especially in text files, a letter has become the next letter along or has become a binary character. Flip the bit and try that. The data's gone out of sync. There's a lot of like bit flipping tricks you can do to get the data back. And if you know the CRC you've got is correct, well, you can use the CRC to tell that you've read the data correctly. Again, if you have 2 copies of a disk, you compare the 2 against each other. And you might have one where track 1 is bad and the other is track 5 is bad, and you combine the 2 together to get one single linear working image. And I've done that on a few disks. I have a perfectly good image of Oak Solutions Genesis Plus from the Learning Curve pack, where the original disks that I'd obtained had various amounts of damage on them. We just merged them together and got a good read. Sometimes you get extremely lucky. There's an area when this decodes, you can see it now. You can see the lighter green here. And what HXC is telling me is that sector is full of the same byte. It's full of, in this case, E5s. It could be full of zeros or FFs. It's been formatted, but it's never been written to. So if I see that on every sector around it, and I see that a sector is E5s all the way up to the middle where we know there's an error, and then is the same byte afterwards, what I can tell from that is that that's a blank formatted sector that's never been written to, and the error in the middle of the sector has caused HXC's decoder to lose sync with the data. So we can, if we know what the data is, we can work backwards from that. And if it's blank, who cares really? We can just leave it as a bad sector, or we can correct it to be a formatted track. It's just completely remastered from scratch. I think generally from a preservation point of view, if we don't have an accurate read of the track, I would prefer to leave it as an error.